all right. Thanks. Thanks for the intro and thanks for having me here. Today I will talk about the dark secrets of stream processing, everything you wanted to know but were afraid to ask. Um, my name is Yinjun. That's the correct pronunciation. And I'm the founder of Rising Wave Labs. So Rising Wave Labs is basically a stream processing company. We have been doing this kind of stream processing for almost 5 years. I started a company in early 2021, actually late 2020 and early 2021. And before starting the company, I was at AWS Redshift, which is a data warehouse, right? And prior to that, I also was a researcher at IBM Research Almaden. So over the last 5 years, we keep developing the stream processing system. And actually, I think this is my third time speaking at the Berlin Buzzword. For the first 2 times, I will always talk about, okay, what are we currently working on, right? What are we currently working on at the Rising Wave Labs, and what's the new innovations we have, right? And now it's already our 5th year, and we actually have a lot of lessons learned, and we know that, okay, actually a lot of things, new technology probably doesn't really work. And probably some new technology looks pretty cool, but you actually have to put a lot of engineering efforts to make it happen, right? Today I'll be talking about focus on this part, right? So if you don't really know what Rising Wave is, then a simple answer is that Rising Wave is a distributed SQL streaming database. Here I just mentioned the stream processing system because sometimes I always have to tell people, okay, what streaming database is, right? But you can just consider Rising Wave as a distributed stream processing system, and it tries to offer the best-in-class stream processing management and analytics experience. As I just mentioned, we have been developing a system for over 5 years, and Rising Wave is from day one, it's open source and under Apache 2.0 license. And now Rising Wave have already been adopted by over 1,000 companies. Actually, I think probably 2,000 or even more. And our customers, including some of the world's largest company, including one of the trillion-dollar company, and banks, security firms, exchanges, or e-commerce, or all these kind of companies in different industries. So whenever we talk about the stream processing, so we will definitely think about, okay, financial services or the use cases. We definitely think about, okay, financial services like payment services, right? We definitely do fraud detection in payment services. And in the capital markets like brokerages, right? Or hedge funds, we actually do the risk control, right? And in entertainment, people do sports betting, they do gambling, they do gaming, they do publishers, right? And e-commerce, where they actually working on the personalized recommendation, price comparison, fraud detection, churn prevention, all these kind of things. So a lot of people, Rising Wave is just like many other stream processing systems. We focus on low latency, like second low latency, and we always do incremental computation, right? If you compare Rising Wave to any other streaming databases, in terms of functionality, everyone looks the same, right? In our customer base, we actually have our prospect, 60% of our prospects compare Rising Wave with Flink and Spark Streaming, 20 probably compare with KSQLDB. Everyone is basically doing the same thing, right? Basically focus on how do we best deliver the low latency data processing, right? But everyone wants to be the best system in the world, right? But over the last 5 years, if we want to clock back to 2020. When we first started a company, we think about, okay, let's just democratize stream processing. We use the word democratize stream processing because we found that at that time, if you consider 2020, right? If you look at Spark, Spark Streaming, if you look at KSQLDB, if you look at Flink, people always say that, okay, stream processing systems are so difficult to use, and stream processing systems were so expensive, right? So actually, at that time, I don't really think that many stream processing systems offer the SQL functionality. Even for Spark Streaming and Flink, well, SQL was still kind of early in 2020, right? So when we started, when we just started a project, we just want to make it super easy to use, and second, cost efficiency, super cost efficient, right? How do we achieve that? So we achieve that through some, we call it design principles, right? So in terms of the ease of use, we focus on SQL, PostgreSQL style SQL, right? Well, we offer Postgres compatibility, which means that you do not need to learn some like a Java API, Python API, whatever API, right? Or you don't really need to learn something like a certain kind of a SQL dialect, right? I have to say that being Postgres compatible is definitely a very good design decision we adopted, because I mean everyone knows that Postgres is nowadays really super popular, right? Every single company wants to replace their existing databases to Postgres, right? And being Postgres compatible allows you to directly integrate their system with with a Postgres ecosystem, right? If you consider all these kind of like data visualization tools, management systems, or the orchestration tools, right? Metabase, Grafana, dbt, dbeaver. Once you are compatible with Postgres, you are definitely you will be able to integrate it through all these kind of like data systems that can talk to Postgres, right? And the second design, so Postgres compatibility is definitely one of the key design decisions we made. And second design decision we made was that, okay, we should have the built-in storage. So in the past, if you look at Flink or Spark Streaming or KSQLDB or even earlier Samza, right, well, probably so-called Storm, right? None of these databases have the state management, built-in storage. So essentially, when I first started working on stream processing, that was around 15 years ago, and Storm was pretty new project at that time. And it actually doesn't really only provides the so-called stateless computation, and it actually relies on, for the first few versions, well, it actually only relies on some external databases to store the storage. And then for Spark, in Flink and in Spark Streaming, they actually adopted their own state management system, right? Well, components, right? In Flink, it actually adopts the RocksDB. But we definitely want to make it more advanced. So in terms of the so-called built-in storage, what do we think about is that you actually have to be able to expose your states to the users. Why? Because it actually brings at least two advantages. The first one is that it actually definitely simplifies your architecture. Why? If you consider you're using, let's say Spark Streaming or probably Flink, right? So all these kind of systems, if they do not really have the storage system, then they are not able to directly consume the data from your upstream jobs, right? Let's say assuming that we have, let's say, a streaming job, right? And you actually want your downstream streaming job wants to consume the upstream streaming processing jobs output. How do we do that? We actually have to put a Kafka in between two different streaming jobs, right? That can definitely complicate the architecture. And because for stream processing, previous stream processing systems, in traditional stream processing systems, they didn't really expose the storage. You actually have to use the external databases like Postgres, like Redis, like MySQL or MongoDB, right, to store your results, right? So that's where people can query the data and people can understand, okay, what the output really looks like. But with a built-in storage that can be queryable by by users. The good thing here that you no longer need to have such kind of complicated architecture, right? You don't need to have a stream processing system, a Kafka, and databases to be stitch all these kind of systems together. You can just have one single system that exposes a concept called material view, and then allow users to directly build material view on top of material view in order to express a very complicated stream processing logic. And because it's queryable, right? The result, the material view result is queryable. You can also allow people to directly serve their applications, right? Imagine that we are running something like a user-facing application. You can directly use a database to serve in this case, Rising Wave, to serve the dashboard or serve the API or serve the application, right? That's definitely one of the huge benefits of having a built-in storage. And the second advantage is also the consistency, right? If you have the different streaming jobs, and the problem here that's the different streaming jobs do not really understand each other, do not really understand the progress of each other, right? So you actually have to figure out, okay, whether two different streaming jobs are consistent or not, right? Two different streaming processing the jobs outputs are consistent or not. But if you have a built-in storage, the streaming job actually are aware of the different streaming jobs are actually aware of each other's progress, so that you can have a way to make sure that everyone is consistent, right? But the result exposed to the users are consistent. How do you do that? Yeah, if you are familiar with database systems, right, where there's a concept called multi-version concurrent control, and essentially using multi-version concurrent control can ensure that all these material views are consistent, right? Consistency is so important. Just imagine that if you are running an e-commerce application, right? And one of the streaming jobs actually calculates the number of items currently in the store, and another streaming job calculates the number of orders received. We definitely want to make sure that these two results are consistent, so that our customers can always place orders whenever, and ensure that they can actually collect their items in the store, right? So consistency is super important, and having the built-in storage is definitely help you to simplify the implementation of your application. So having a built-in storage is our second design decision, and third one is And for the Postgres compatibility and the built-in storage for all about ease of use, and how about cost efficiency? To facilitate to achieve the best cost efficiency, we actually adopt the architecture called S3 as the primary storage architecture. And using this architecture, we could always achieve pretty good runtime performance, achieve instant failure recovery, and achieving the elastic dynamic scaling. Dynamic scaling. So actually, my last year's talk in Bread and Butter was all about how we build S3 as the primary storage architecture. But we actually have a lot of lessons, and I will definitely cover that later in this talk. So if you're not familiar with S3 as the primary storage architecture, then just imagine that imagine that we want to have all the computation running in EC2 while having all the storage stored in the S3, right? That's the so-called S3 as the primary storage architecture. And many other systems, modern data warehouses, and probably modern OLAP databases also adopt exactly the same architecture, like Snowflake, right? And sometimes people say that's why it's so-called decoupled container storage, or so-called shell storage or tier storage architecture. Having the S3 as a primary storage architecture definitely bring a lot of benefits. yeah, one of the benefits is actually definitely we do not really need to consider how we can partition the data, right? Let's say imagine that if you're using something like existing systems like Flink, right? You actually need to consider how we can partition this through a sharded data state into three pieces and place states in different machines, right? But with the S3 as the primary storage architecture, you actually do not think a lot about that because we could you actually still have to think about that because it definitely allow you to have a better workload balance. But essentially, the key idea is that you actually do not need to. You actually do not. You can. You actually do not need to partition the states because anyways we could put the states in the S3 in the S3, right? And with this architecture, we could actually achieve second level fault tolerance. How could we do that? Let's imagine that one of the node failed, right? With the states persisted, right? Not cached, persisted in the compute nodes. You actually have to, once the node failed, you actually have to recover the state from the last checkpoint, right? And the checkpoint is actually stored in persistent storage. You actually have to reload the checkpoint from your persistent storage, right? And then do the recomputation. But if we have the S3 as the storage architecture, primary storage architecture, then a lot of things could be changed. Why? Because the state is actually persisted in the S3. So that's once the node failed, the only thing lost is just the cache, right? Cache is just okay, it's right away if it's crashes, well that's fine, right? So you could just reboot another machine and ask a new machine where the data is stored, right? Okay, it's stored in some buckets in S3. Right, and then the new machine could just read the data from the state without without going back to the previous checkpoint, right? So that's a huge difference. And with this architecture, we could definitely achieve the second level failure recovery. And similarly, we could also achieve the second level elastic scaling. How could we do that? Yeah, very similar concept. That is, once we want to scale in, let's say scale out from one machine to 3 machines, we do not need to reload, ask the streaming job to reload from the checkpoint, right? To do the state migration, right? To migrate from the one machine to 3 different machines, right? The only thing we need to do is to create the 3 new machines and tell the 3 new machines that, okay, where the state is stored, right? They can directly fetch the data from the S3, right? So that's the beauty of the S3 as primary storage architecture. Everyone will tell you the same thing, right? So if you go to Snowflake, if you go to, let's say, many other systems, they will tell you how great S3 as a primary storage is, right? And I think recently Flink also adopted the exactly same architecture in Flink 2.0, 2.0. But I think we're still kind of early. So to a brief summary here is that, okay, we actually adopted for RavenWave, we adopted 3 key design decisions. The first one is Postgres compatible, and second one is building storage, and third one is the S3 as the primary storage architecture. So if you so that's the all design decision, and we spent 5 years developing the system sticking with these 3 design decisions. Then people will say, okay, that would be great, right? And your system can run smoothly, and I believe that you can achieve super easy, the so-called ease of use and cost efficiency, right? But I have to say that the devils are in the details, right? Once you start implementing and onboarding your customers, right, and onboarding a lot of new use cases from different domains, you will immediately find that a lot of pain points. And I could actually summarize the pain points into these 5 categories: the performance, cost, backfilling, consistency, and isolation. I'm not sure whether I can cover. I have enough time to cover everything, but I can definitely cover. Discuss some of them in detail. Let's just talk about the performance first. So S3 as the primary storage architecture is definitely great, right? So everyone talk about that, but I have to say that S3 access is so slow, so slow. So if you read the documentation from AWS, they will tell you that the normal latency is around, I think, probably 30, 40 milliseconds. And S3 Express is definitely, I don't really think that's a pretty successful project, right? Well, because we know that S3 Express, not many people talk about that. But people still use, because S3 Express is so expensive compared to the normal S3. But for normal S3 bucket, the normal latency is around probably 30 to 40 or 50 milliseconds. But the thing here, that's it's just it's not a P99, right? In some worst cases, the latency can be as high as 200 to 300 millisecond latency, right? That's definitely too slow. Well, essentially, if your latency is around 40 to 30 milliseconds, 30 to 40 milliseconds, then it's still kind of slow for the stream processing system. Why? The reason here is that for stream processing system, let's imagine that we are doing a streaming join, right? Let's say that for every single second, we have 1,000 new event comes in. For every single event within this 1,000 events, we probably have to do we definitely want to do a match, right? Well, to check, okay, whether it's a match the events, right? So if for every single second we have to spend around, let's say 50 milliseconds to fetch the data from S3, you could imagine that definitely will have a pretty long backlog, right? So it's definitely not tolerable. So that's about the performance. S3, so the summary here, so if we have put everything as a S3, then definitely performance will be a big issue. And then how about cost, right? The S3 looks so cheap, right? So it's just 23 terabytes. You only need to pay for $23 per terabyte per month to AWS, right? But I have to say that this is just a storage size, right? This is just the price of the S3 storage. But what people usually miss is the S3 access cost. S3 access cost is actually extremely expensive. So in some of our in production workloads, we could see that 50% of the total cost is actually goes to S3 access instead of CPU. Actually, in some worst cases, it can be actually way more expensive compared to the CPU's cost, right? And another tricky part here is that different vendors actually have very different pricing strategy. Like this is the pricing storage here. I just showed you the pricing strategy of AWS, right? In AWS, for every 1,000 requests, you actually have to pay 0.05 around 0.5 cents, right? To the to AWS. But imagine that for every second you have to access the S3 for 1,000 times. Then how much time we should pay for AWS every single month? You can do the math, right? Essentially, what we can see here that we actually, in some worst cases, we actually have to pay thousands or even tens of thousands of dollars to AWS just for accessing data, right? And different vendors have different pricing storage. So if you have build a system in different storage, you may feel that in some clouds you may feel that the S3 cost is so cheap. Or even in some clouds where they didn't even charge you for S3, right? But in AWS, it can be very expensive. I think in Oracle, they didn't really charge you for this. And this is Alibaba Cloud's pricing. I know that probably not many of you guys will speak in Chinese, right? Read Chinese. But what I can translate for you is that okay, actually AWS, Alibaba Cloud doesn't really charge you for the put and get, right? It says that it's free. And only above 5 million requests where they'll charge you some small amount of dollars. So what I want to share you here, that's okay. Essentially, for different vendors, they actually have different pricing storage. So if you build a system in different clouds, you may have different cost results, right? So to summarize, using S3 as the primary storage could be the good idea, but the problem here that's where S3 is too slow, and for every single request it could be like cost 200 or even 300 millisecond latency, and it could be so expensive, right? Because in AWS, in some certain kind of cloud providers, you actually have to spend a huge amount of money to just get the data or put the data from and to S3, right? How do we fix the problem? So definitely the idea is that okay. Anyways, for EBS, local machines, right? EC2 has the memory, right? And we can definitely try to get a bigger machine, right? Definitely that's a great idea. And but for sure, you actually have to pay more money, right? And the other strategy we could have is that okay, we can actually use the local SSD, right? Because in AWS, we could definitely directly mount the NVMe SSD to a local disk, right? To local machine, right? Is that a good idea? Well, I have to say that if you just build a specialized system for your in-house usage, then probably it's good. But if you want to build a service, then definitely it's not a different story, right? For RagingWave, in our case, RagingWave Labs, right? Well, we actually build a service for our customers, right? Not for us, right? So essentially, we found that using local SSD is not a good idea. Why? There are at least 3 reasons. The first one is that, so first of all, NVMe SSD is definitely fast enough, right? Well, definitely in terms of latency, I have no problem with that. But if you consider about using NVMe SSD in production for your customers, then you have to think about okay, first, not all the EC2 instances can attach local SSD. For example, if you just have a small streaming job, then you could not, you probably only need a machine with, let's say, 4 CPUs, right? But for that kind of type of machines, AWS probably does not really allow you to attach the NVMe SSD to your 4-core machine, right? It's not possible. And second one is that local SSD is actually very expensive. Why? Because in AWS, the machines that can attach local SSD is actually around 20 to 25% more expensive than the machines that could not attach an NVMe SSD. So if you imagine that you have, let's say, 32 CPUs, right? So you actually have to pay 32 CPUs with local NVMe SSD. It's actually 20 to 25% more expensive compared to a machine with 32 cores that could not attach a local NVMe SSD. So that can be very expensive, right? And the third reason here that actually the cloud providers, actually for different cloud providers, their disk specs is actually very different. If you want to migrate them a service, we definitely have a rich experience in doing this. Migrate a service from, let's say, GCP to AWS, you will immediately find that you actually have to retune your system because the disk spec is so different. So for all these kind of reasons, we think that it's actually not a good idea to use local SSD. So what's the solution here? We actually use EBS. I know that's what people are saying that, okay, why EBS, right? EBS is so-called ND pattern, right? so if Neon, Nikita from Neon, right? When Neon just got acquired by Databricks, right? So he actually have a tweet about, okay, people should not use EBS when building the cloud native infrastructure service. Too expensive. But my argument is that it's actually not expensive. Why? Because if you so here, what he actually means is that if you use EBS instead of S3 to build a service to store your persistent storage, to serve as the persistent storage, then it could be very expensive. But here, what I'm talking about is to use the EBS as the cache to replace the local SSD. So that's a difference, right? So for Nikita's case, he is actually right. He's not wrong, but what he actually means is that you should use S3 instead of EBS to store your persistent storage. Well, here I'm arguing that essentially you should use EBS instead of local SD to serve as the caching layer for your computation services. And essentially for EBS, the performance is actually good enough. Right, because for EBS, the latency is around. I don't really have the number here, but sometimes it could be like a single digit millisecond, or sometimes it could be like probably 2 digits millisecond. But essentially, for stream processing jobs, what we find here that it's actually good enough to power your low latency stream processing. What do we observe that with EBS, we can definitely achieve the latency as low as 100 milliseconds. There's no issue with that. So here are some results, right? So we actually developed the Rising Wave with the local. We actually compared the Rising Wave without a local disk versus a Rising Wave instance with a disk cache. And what we can see here that this is the number of requests sent to the S3. What we can see here that once we enable the disk cache, we could drastically drop the S3 access from 2,000 operations per second to around 400 operations per second. That's a great job. And essentially, with this job, we actually could reduce the S3 latency. The S3 access cost from $20 within, this is around I think how many hours? Probably around 20, right? Yeah. No, sorry, it's not 20 hours. It's 12 hours, right? For 12 hours, we actually have to without the disk cache, we actually have to spend $20 to S3, but with the S3 disk cache enabled, we could drop the S3 cost from $20 to $3, right? This is a huge saving in terms of the S3 access. And definitely S3, the other benefits brought by the EBS disk cache is the better performance. So this is if you are familiar with stream processing, this is the very famous stream processing benchmark called Nextmark. And here I didn't really compare with any other system. We just compare Rising Wave with Rising Wave. For the green bar, it's the Rising Wave result. Rising Wave throughput. It's a throughput without this cache. And the orange bar shows the Rising Wave throughput with the disk cache. What we can see here that's okay for the stateless jobs, right? So for these queries, if you have the stateless jobs, then definitely enabling or disabling the disk cache doesn't really matter. But once you have jobs like streaming joins, for example, this query, and that query. Once we enable the S3, once we enable the disk cache, we could drastically improve the performance by 2 times or even 3 times. Why? Because it essentially reduce the frequency of accessing S3, right? So to summarize, with the S3 with a disk cache using with the EBS powered disk cache, we could drastically reduce the S3 access cost and improve the performance. So yeah, this is just some of the improvements we made in terms of the performance and cost. And I just mentioned that we also did a lot of improvement in terms of backfilling. We actually encountered a lot of issues with backfilling, and, consistency, and isolation. I know that's why I don't really have enough time to cover everything. But one interesting thing I would like to share is that I could probably skip this backfilling part. I have to say that backfilling is definitely one of the most challenging topic in stream processing. But here, what do we find? We could find. Yeah, I could probably skip this part. Yeah. So yeah, I could. What I want to show here is that for backfilling. With the S3 as the disk cache, with S3 as the primary storage architecture, we could actually help people to scale out the backfilling process just during the backfilling stage. How? Because we actually have the states stored in the storage, right? Or this S3, right? So that we can scale in and scale out dynamically. Okay, so So one last thing I want to talk about before wrapping up this talk is the consistency. People will. This is a very interesting topic because everyone will say that yeah, we always want to have a consistent result, but people should always know that you actually have to pay the price to get a consistency. So in a database, some people call it internal consistency, which means that for every single materialized field, the results are consistent, right? So in a database context, essentially all these the materialized fields are in the same version, right? But what I want to tell you is that essentially consistency actually can fail a system. Because why? Because for different materials used, the computation complexity is actually different, and the amount of data ingested into the materials used can be very different. For example, in this case, let's assume that for these two materials used, they are having the same computation logic, but one materials you have a lot of data comes in, right? A lot of input, while the second materials you only have, let's say, very few events come in. If you want to ensure that the consistency between these two materials used, then the problem you will immediately encounter is that essentially you will find that the computation process is different, right? And which means that you have no idea of, which means that if you want to if you want to have the user to see the consistent result, you actually have to spend more resources for the material field on the top, right? So that can encounter a lot of computation, workload balancing, and some other issues. So what our thoughts here is that essentially when you build a stream processing system that guarantees the consistency, you probably should think about how you can do the workload isolation, or how you can or even allow people to loosen the consistency requirements. Okay, so yeah, I know that's why I'm running out of time, but here to summarize this talk, we never regretted adopting these design decisions like Postgres-style SQL, being Postgres compatible, having a built-in storage, having S3 as the primary storage architecture. But we have also put a lot of engineering work to fix the challenges around performance, cost, backfilling, consistency, isolation, and many others. So just when you build a system, don't just think about, okay, we can just adopt a certain kind of architecture or design decision, and every kind of a challenge could be magically resolved, right? You actually have to spend more engineering work to fix everything around. All right. Yeah, that's all my talk, and thank you. So, yeah, thanks.
Thank you.